All right, these are the answers to this accumulating worksheet here. And we're given a function capital F equal to the integral from 2 to x of little f. And little f is this graph over here. One thing to kind of note right away when you see these accumulating graphs is to know that the derivative then of this accumulating function would be the derivative of this integral, which would just be that little graph there. So in other words, the graph you're seeing is the derivative of capital F, okay? And connecting that right away helps answer a lot of these questions. So for A, it says find capital F of 0. Well, that's no more than just putting 0 in for x. It's going to be the integral from 2 to 0 of little f. And so that means we're going to find the area from 2 back to 0. So that's this triangle. 2 times 2 is 4, divided by 2 is 2. But we're going from 2 back to 0, so this would be negative 2. So not a hard problem, but you want to be real careful. Don't make a silly mistake. F of 4, same idea, would be the area from 2 to 4 of little f. And so if we went from 2 to 4, it's this quarter circle now. That has a radius of 2. So pi times 2 squared is 4 pi. Take a quarter of that, and it would just be pi. So that's all we're doing on there. Determine the interval where f of x is increasing. So f of x is increasing when its derivative, which is little f, is positive. So the AP wants to see that, that's something we've written many, many times already, but it wants to see this connection between the big function and, this, what you're seeing here. This is positive from 0 to 6. So 0 to 6. Find the critical numbers of f of x and determine if they're minimum, maximum. So first off, critical number is where f prime, which is little f, is 0 or undefined. And that occurs at x equals 0 and 4. 0 and 4 are the places where our derivative is 0. So x equals 0. We'll start there. If I look, the derivative switches from negative to positive. That means the function's switching from decreasing to increasing. So x equals 0 will be a relative minimum. F prime x, which equals little f, switches from negative to positive. Okay? And then x equals 4, if you look, the derivative was positive and it stayed positive. So x equals 4 is neither. F prime x, which equals little f of x, is positive before and after x equals 4. Or you could say something about it didn't switch or something like that would be fine too. Find the absolute extreme value of f of x and the x values where they occur. So what we want to do when we find the absolute max or minimum, we want to take our endpoints and any critical points that might come up. So we'll do this down below. Okay, we're going to bring this down here. And we're going to set up our intervals, or not our intervals, but what are our candidates? Should we be testing? We should be testing our endpoints, the start and the finish, and we should test our critical points, so the 0 and the 4, okay? And the nice thing is we already found f of 0, we already found f of 4. F of 0 was negative 2, f of 4 was pi. We found those earlier, okay? So as far as negative 2 goes, if we went from 2 back to negative 2, it would be this area and then this area. Well, you can see that those are going to cancel each other out, right? And so f of negative 2 would be 0. Because again, the areas that we're talking about kind of cancel each other out. As far as f of 6 goes, that would be that quarter circle, which is pi, plus this triangle. 4 times 2 divided by 2 would be 4. So at 6, we're going to have pi plus 4 more. So when I'm looking at my options here, the minimum would be this one, negative 2, and the maximum would be this one. So the absolute maximum value of this function is pi plus 4. That occurs at x equals 6. The absolute minimum of this function is negative 2. That occurs at 0. Okay. Now, find the x-coordinates of the inflection point. So inflection point is when our derivative, which is little f, switches from increasing to decreasing or decreasing to increasing. When the derivative is increasing, our original function is concave up. When our derivative is decreasing, the original function is concave down. So wherever that switch occurs, even if it's a sharp turn, doesn't matter, that's a point of inflection. So we're going to have a point of inflection at 2 and at 4. Those are where our switches occur. And again, to justify, you just simply say what we said here. It's anywhere that our derivative switches from increasing to decreasing or decreasing to increasing. And then the final one says, where is this graph concave down? So that we kind of already answered that. That's when our derivative, which is little f, is decreasing. When your derivative is decreasing, your original function is concave down. This derivative is decreasing from 2 to 4. So that walks you through what could be an AP kind of problem, something like this here.